All right, well, thanks. So I'm going to talk about scalability, not scarcity, how we can ensure long-term equitable access to blockchain technology. So one of the great things about working on an open source project and working at a nonprofit is that we don't have to worry about paying dividends. We don't have shareholders to be accountable to. At the end of the day, I'm accountable to one thing, which is the mission, right? And Stellar's mission is to create equitable access to the global financial system. And I think that, over the last 11 years, we've done, a huge amount and developed a whole bunch of kind of features of the network that directly support this goal, right? We have kind of the best network of on-off ramps of any blockchain, pretty much the lowest transaction fees of any major blockchain. We have a really high reliability. I don't even remember, before COVID, the last time we had any amount of downtime, and it's only happened a few times over the whole 11 years. And of course, we have very good documentation and tooling, kind of stuff Lee was just talking about. And so I think that stuff's going to continue to happen, and we have a great team, and we have a great community. And so that stuff doesn't worry me anymore. And so what I'm spending my time thinking about these days is what happens when we start to see some really high volume applications, right? Somebody comes on Stellar and wants to, compete with WeChat Pay and credit cards or NASDAQ, really, really high volume stuff. Or someone wants to develop smart contracts that are way more computationally demanding than what we have today. I mean, I have some experience myself in research where I worked on this project where we did sealed bid auctions on a public blockchain. We had a standalone implementation that was fantastic, and then we said, oh, let's see what happens on Ethereum, and it costs $200 to place a bid, which for you won't even win. So it was just kind of a non-starter because it was too computationally expensive. So I think the risk, if we are successful and don't worry about it about this today, is that we can end up with computational scarcity on the blockchain that will end up increasing the cost to transact on the blockchain, limiting what we can do and the amount of innovation we have, and ultimately kind of decreasing competition because there'll be fewer entrants to the marketplace, which ultimately can kind of undermine the mission, right? And so in this talk, I'm going to talk about why actually blockchains can be way more scalable than we think. So as a disclaimer, I'm not telling you about stuff that's necessarily going to be in Stellar, right? It's not a product roadmap or whatever. These are research results, but they're research results that are informing my thinking as I'm kind of thinking about how to keep Stellar really accessible for the long term. All right, so how did we get here? Well, really, blockchain is kind of the intellectual descendant of this old idea in computer systems called a state machine replication, right? It is very simple. You agree on a series of transactions in order, and you have a consensus protocol, so everybody agrees on what the transactions are and what order they happened in. And then you have a bunch of replicas that they all start in the same state, and then they all execute the transactions deterministically, and so they maintain the exact same state, right? And one kind of inherent problem with this model is that because you're logically executing these transactions one at a time, if you implement this naively, you're kind of limited to the throughput of kind of executing everything on a single CPU, and there's only so much single thread performance you can get out of a computer. So when we moved to blockchains, right, there was this huge innovation of Bitcoin, which was, hey, let's do this on a decentralized consensus protocol, which at the time, in 2009 or whatever was proof of work. Obviously, I developed my own consensus protocol for Stellar, and this was more expensive. So now we're going to amortize the consensus over these blocks of transactions, right? Hence the name blockchain. But it's essentially the same model, right? These blocks logically have transactions in order, and you're supposed to execute them in order. And so the kind of deterministic in-order execution can limit the performance of the blockchain to what you can get out of a single CPU, right? So, of course, a lot of people now are talking about increasing TPS and going faster. And so how do you actually get more performance out of the system? Well, one thing you can do, right, is sharding, right? This is very simple. If one blockchain can execute 1,000 transactions per second, well then 100 blockchains could execute 100,000 transactions per second, right? And so, of course, sharding works. The problem is now if you need to do cross-shard transactions, those are going to become a bottleneck, right? And so it only works if you have certain patterns of transactions. Another thing that people are looking at is, of course, optimistic rollups, right? And like these do get more scalability, but you have to kind of rely on people to kind of object when there's cheating involved, and you have to kind of lock up capital to make sure you can punish people who cheat and reward people who report it. And so that all increases the risk, and it kind of bounds the value of kind of sensible transactions that you can do to the amount of capital that's locked up, because if kind of the amount that's at stake is much less than the amount you can steal, you have to worry people will steal stuff. So then there are like ZK rollups, right? And these things are almost a misnomer, because they're not actually, the zero knowledge isn't actually zero knowledge, it's just they're borrowing techniques from zero knowledge to get kind of very, very good asymptotic scalability, right? So they're fairly high constant factors, but you can really, theoretically do like an arbitrary number of transactions and kind of a fixed amount of state. And the problem with these is that they're just extremely complicated, but they're definitely motivation that people are worried about, like how are we going to scale this transaction throughput. So the most kind of maybe straightforward and appealing way of scaling blockchains is, well, like, let's just make our validators faster. And the way to do that is through parallel execution, right? Use multiple CPUs. And this is kind of what like Solana and Aptos and Sui do. And as of a few days ago, Sorbonne now actually has support for this. It just needs to be configured by a vote of the validators. But there's still a problem here that it only scales if transactions don't conflict. Any conflicting transactions, and you're going to have to execute them one at a time. And again, because we're in the blockchain space, we kind of have to deal with adversarial workloads here. And so another limitation with kind of all of these approaches is that none of these can really deal with adversarial workloads, right? In sharding, you could have all these like cross-shard transactions. With parallelization, you could have a lot of conflicting stuff. And none of these can kind of grow quickly or shrink to accommodate surge capacity, right? So, a common thing might be like in the US, a lot of people pay their taxes like April 15th, right? So you can imagine like everybody hitting like this one bank account of like the Internal Revenue Service, like that would be scaled terribly on one of these systems with like concurrency as it exists. All right. So before we get on to some of these research results, I do want to say that Stellar's been doing some really good stuff for performance. One of the things we're doing now is like working on overlapping consensus with execution. If we get more blocks per second, that'll be more transactions per second. As of the last release, we can now keep the live state in memory, which vastly reduces or eliminates database reads. We're caching parsed WASM modules, so that, again, saves a lot of overhead. We're looking into using a just-in-time compiler for the WebAssembly, which, again, will increase performance. And as I mentioned, we now have parallel execution deployed, and pending a vote of the validators will actually be used in practice. And I recommend that you come back to this stage at 2:55 and 3:25 tomorrow to listen to Garen's and Marta's talks, and they're going to tell you about some of this really great performance work. But at the end of the day, scalability is not a number, right? Scalability is about the shape of a graph. And so if I want to kind of like worry about Stellar in the long haul, no matter how many transactions we need to make sure we can accommodate that, we need to make sure that the shape of the graph is right. And the only thing that really gets us a better shape of a graph as opposed to like a one-time win is parallel execution. So what's the problem with parallel execution? We just enabled this, and I already told you we have support. Will this solve the problem? Well, here I've got a graph of a measurement we did at Stanford, just kind of a 4-node system. And here we're looking at block STM, which is like a pretty well-regarded like optimistic concurrency control system for processing transactions. Now, if we just kind of zoom into like the lower left portion of the graph, and you look at like 1, 2, 4, 8, 16 CPUs, it looks pretty good, right? It looks like it's kind of scaling when you have 1 million accounts like paying random accounts. But the problem is it kind of tapers off, and beyond 16 CPUs, like it doesn't scale anymore. And 16 CPUs, like that's practically a cell phone these days, right? Like servers have a lot of CPUs these days, right? So we need to be able to scale way beyond that. And then there's a worse problem, which is that what happens if you have like just 2 accounts paying each other? And so that's this lower line here. You can barely see that it's like almost looks like the same as the x-axis, right? Because we're getting no speed up at all because all these transactions are conflicting. And yet that's exactly what would happen if everybody were paying their taxes, on April 15th. All right, so obviously these conflicting transactions are a huge problem. Like, can we design a blockchain so that the transactions are conflict-free by design, right? And one clue as to how we could get there is a seminal operating systems paper by Austin Clements et al. In SOSP 2013 called the Scalable Commutativity Rule. And what they said in this paper, and they actually proved it, is that whenever interface operations commute, meaning their ultimate result doesn't depend on which order you execute them in, then they can be implemented in a way that scales. And so that's kind of the necessary and sufficient condition in an API to make sure that you can implement this scalably. So, so blockchains, you know, they reach consensus on blocks of transactions. What if we could make it such that the blocks, of course, are happening in order, but if within a block, the order of the transactions didn't matter. Like any two transactions in a block commute, and we can just kind of execute the thing. If you could do that, then you could literally execute every single transaction in a block on its own CPU in parallel. You could basically like scale up to like as many CPUs as you have transactions practically. Of course, the challenge is we need a new API that's going to guarantee commutativity. And this is where I'm really excited by some of the recent research results. So let's look at a particular problem, and that's a distributed exchange. You want an asset exchange. It's a very well understood problem that in order to make markets work well, we want a continuous double auction where people come in with limit orders, and when the limit orders cross, you know, you fill them, right? Standard problem. Turns out this is like a worst case for parallelism, right? Because if you think about it, every operation is like modifying the shared data structure with this, which is an order book, and so locking that order book is going to serialize every single transaction, right? But there are other ways of structuring markets that actually make trading assets commutative. So in particular, there's this old econ paper by Arrow and DeBrove in 1954. It's often given to like first-year econ PhD students, in which they propose using a batch exchange markets, right? And they propose this primarily for economic reasons, but the idea is you have a bunch of assets people are trying to trade, and what you do is you take a batch of offers, and you're going to come up with a batch of trades, and within the batch, you assign a fixed valuation for every asset. So asset A is going to have price PA. Now, what's the numerator asset? What's the units of PA? It doesn't matter. It's just some made-up thing that only needs to exist for this one batch of trades, right? And so now anybody who wants to trade asset A for asset B is going to pay the price of the valuation of B, PB, over PA, right? So originally, they proposed this for economic benefits because, you know, it eliminates cyclic arbitrage. Like, you don't have to worry if you're trying to get between, you know, Nigerian naira and Philippine pesos. You don't have to worry about which intermediary assets to go through. It also increases liquidity because you can end up trading even when you're not trading with a specific person because no one wants to take the other side of your specific trade. And it also eliminates kind of in-block front running and MEV because everybody's trading at the same price, so it doesn't matter, like a miner like can't, you know, like reorder the transactions, like the effect will be the same. But from the point of view of scalability, we have an even bigger benefit, which is that because all the trades are happening at the same price, all the trades are commutative, right? Like, you're gonna trade asset A for asset B. Like, I don't care in what order you do that. I know what price you're doing. I know exactly how many A you're gonna pay and exactly how many B you're gonna get. And so, So Jeff Ramsayer, who's actually in the audience here, had this brilliant idea when he was working on his PhD that what if we applied these Arrow-DeBrove exchange markets to the blockchain in order to make trading extremely scalable, right? And so the way this works in a blockchain context is you kind of execute a block in two phases, right? The first thing you're going to do is you're going to look at all the trades, you're going to figure out kind of which ones are in the money, and you're going to compute these valuations for each asset. So in this kind of example that I'm giving you here, maybe we decide the price of US dollars is 9, the price of euros is 10, the price of yen is like 1/15, right? And one of the key innovations is that nobody knew how to compute this efficiently enough for very large order books, or like without doing kind of rounding that was bad. And kind of Jeff figured out how to do this really efficiently and scalably. And the second thing you're going to do is you're going to actually trade at whatever the quotient of these valuations is. And so conceptually, you're kind of taking, like, if this red trader up here is going to basically sell 10 USD to the market for this imaginary numerator asset, and then it's going to use that numerator asset to buy 9 euros back, right? And what Arrow and Dubrow showed is that there always exists a unique set of valuations that clears the market. In other words, there's going to be no surplus debt in the SpeedX market itself, and the traders themselves are not going to be left with any of the imaginary numeraire asset at the end, right? So we don't have to worry about that. So this turned out to work really well once he implemented it here. So here I'm showing you how this scales with 6 threads, 12, 24, and 48. And you can see on the x-axis here is the size of the order book. And all the previous approaches to computing these valuations were at least quadratic in the number of open offers, right? And there is a log factor here, but you can see it just kind of disappears at scale here. And so this, we're talking about 250,000 trades per second, right? So these are some really good numbers by kind of contemporary blockchain standards, right? No DEX can do anything like this today. All right, so what about arbitrary smart contracts? Well, why is it that order matters when you're executing smart contracts? Well, the main reason we care about ordering is in order to decide kind of which transactions are valid, right? For example, if I send a bunch of payments, they're going to overdraw my account. We need to decide that kind of the first few payments are valid, and then once I run out of money, the remaining payments will not be valid so that I can't have a negative account balance, right? Or if there's a unique NFT, then only the first buyer should be able to get that NFT, right? And so again, this is a result that Jeff had, which is that why not have validators enforce validity at the block level instead of at transaction granularity? So this works, this blockchain that he prototyped called Groundhog, is that have the proposer kind of guarantee that all the transaction side effects in a block are commutative. So at the end of the block, it doesn't matter in what order you executed things. And also, you want to guarantee that there's some order in which the transactions were valid, right? But that doesn't mean every order in which you execute the transactions will be valid, at all intermediary points, right? So an example would be, let's say that you have byte strings as one of your abstractions, and you have 2 transactions that write to a byte string. Those 2 transactions, they need to be writing the same value to that block string, otherwise they conflict and the order would matter. And so it's up to the proposer to make sure that you can't include the second conflicting transaction. If they're trying to write different values, you have to defer one of the transactions to a subsequent block, right? But of course the validators will check that. And so that's the high-level model. It turns out that with the right abstractions, this model is highly expressive, right? And so as an example, one of the core abstractions in Groundhog is non-negative integers, right? So adding to and subtracting from an integer, those are commutative operations. It doesn't matter what order you do them in. As you can imagine, if you have some non-negative integer x, you can have a bunch of transactions that are they're subtracting 5, they're adding 10, subtracting 10, adding 5, and so on. Depending on the order in which you do this, there's definitely going to be intermediary points at which the value of x is negative. But when you kind of add these all up, the net effect is that you're subtracting 5 from this number 5. So the effect of applying this is to make x 0, which is non-negative, and so that's okay, right? And so this is, of course, useful for tracking account balances, because now you make sure the account doesn't go negative. You can also implement semaphores if a smart contract wants to do its own synchronization, collateral limits, or just kind of any place you need general linear constraints. So how does it perform? Well, check out these light blue lines compared to block STM that we saw a few slides ago, right? Now, going all the way up to 192 hardware threads, we are getting really good scaling, right? We can get up to 800,000 payments per second. And not only that, but look at the conflicting case with 2 accounts, it actually does better than the case with 1 million people paying 1 million people, which is actually the hard case. But now it's easy because actually you need kind of fewer public keys and stuff to verify in your cache and stuff, so we get a little performance boost from that. All right, so one final result I want to tell you about. This isn't a scalability one, but it's a performance one that I think is very important in terms of kind of equitable access to the blockchain, right? One unfortunate thing about the blockchain community now is that there's 2 classes of developer. Those who can land PRs and change Stellar Core, and those who just kind of have to use the features in Stellar Core and might need to wait for Stellar Core to implement some kind of feature. And so one of the things that Zach Yedidya and Jeff and I showed in research is that you can actually, it's practical to make smart contracts that are in raw machine code, either x86 or ARM, right? And the way you do this, you have to compile with a few special flags to the compiler, but this is supported by existing compilers. Then you rewrite the assembly language to guarantee that the output code will be safe, like it won't access memory it's not supposed to access, that it's metered, so you can deterministically decide if it is using too much gas or not. And that it's easy to check that this is the case. Then there's a tiny 2,000-line program that verifies the binary code is safe. And then you can execute these raw machine language smart contracts, right? Now, the caveat, there's many challenges to deployment. But when we do this, we start getting really good performance. So now I'm showing you Groundhog with this deterministic client decal compared to WASM time. And maybe this isn't very exciting if all we're doing is payments and most of the work is verifying digital signatures, because verifying the digital signatures happens natively, right? But what happens if you don't like that, you want to use some new crypto algorithm, like we're using ED 2519, maybe you want like BLS signatures because they threshold more easily and like, you know, they're not supported in your native blockchain. Then you need to actually implement your crypto in WASM. And then we start to get a huge difference in performance, right? We're getting like over twice the performance from letting you actually specify the machine code for your transactions. And here I'm comparing to a JIT, which has like a huge attack surface and a lot of complexity. If you wanted something comparable in security, you'd need like an interpreted WASM runtime, so something like WASM 3. And now you can see that we're just smoking the performance. Like it would be unusable to try to implement your own crypto using something like a WASM interpreter, right? And yet we can get the security of an interpreter with more than twice the performance of a JIT. All right, so in conclusion, Stellar's already primed to enjoy better performance. So now I think we need to think about scalability, right? It's time to move on from transactions per second to payments per second per CPU, or if it's not linear, at least like how many CPUs you need to get like an arbitrary target of payments per second. We have existence proofs that we can actually achieve this scalability through commutative APIs, and an existence proof that we can actually make kind of crypto more egalitarian by letting people supply their own machine code, albeit with some open questions around that. So I want to end with kind of a prediction and a question for everyone in this room. So my prediction is that if we can end computational scarcity on-chain, that's going to unleash an unprecedented wave of blockchain innovation, because we're going to be able to do all these things that right now they would just cost too much gas, including at-scale competition with traditional finance. I think like when we're going to get to like seriously competing with credit cards or like WeChat Pay or whatever, like we're going to need a lot more scalability on layer 1. And so my question now is, what would you do if we could give you 1 to 2 orders of magnitude more on-chain computation for your smart contracts? Thanks.
That was great.